The Celestial Beacon, Henrietta Leavitt and the Universe's True Scale. Part 1. The Human Computers of Harvard, Early 20th Century. The turn of the 20th century marked a period of immense scientific discovery, yet for many women aspiring to careers in science, opportunities were severely limited. Universities like Harvard often relegated female graduates to roles that were more akin to clerical work than groundbreaking research. It was within this environment that the Harvard College Observatory, under the visionary directorship of Edward Charles Pickering, created a unique, albeit subtly exploitative, solution to process the mountain of photographic plates streaming in from telescopes around the world. These women, often highly educated, were hired as computers, human calculators tasked with meticulously examining, classifying, and cataloging the stars, nebulae, and galaxies captured on glass plates. They worked long hours in a room filled with flickering gas lamps and the faint smell of chemicals, hunched over microscopes, meticulously recording data. Paid a pittance, often less than half of their male counterparts, these women performed work that was foundational to modern astronomy. Among them was Henrietta Swan Leavitt. Born in 1868 in Lancaster, Massachusetts, Leavitt displayed an early aptitude for mathematics and a deep curiosity about the natural world. She attended Radcliffe College, then the Society for the Collegiate Instruction of Women, where she cultivated her interest in astronomy. After graduating in 1892, a severe illness left her profoundly deaf, profoundly impacting her ability to communicate in an era before widespread hearing aids or inclusive practices. Yet, her determination to pursue a scientific career remained unwavering. In 1895, Leavitt began volunteering at the Harvard College Observatory, eventually becoming a permanent staff member in 1902. Her role was precisely what the job title suggested, a human computer. Her specific task was to study variable stars, stars whose brightness, luminosity, fluctuates over time. She focused particularly on Cepheid variables, stars that expand and contract rhythmically, causing their brightness to vary in a predictable pattern. Her work involved painstakingly measuring the brightness and period of thousands of these stars, a task requiring incredible patience, precision, and a keen eye. While the work might have seemed mundane to some, Leavitt's meticulousness and sharp intellect would soon unveil one of the universe's most profound secrets. Part 2. The Discovery, Leavitt's Law, 1908 to 1912. Henrietta Leavitt spent years diligently cataloging variable stars. Her primary focus was the Small Magellanic Cloud, SMC, a dwarf galaxy orbiting the Milky Way, visible primarily from the southern hemisphere. The SMC was particularly useful because all the stars within it are roughly at the same distance from Earth. This crucial fact meant that any differences in their apparent brightness were directly related to their absolute brightness, their true intrinsic luminosity. Through her painstaking observations, Leavitt noticed a peculiar pattern. By 1908, she had identified 1,777 variable stars in the Magellanic Clouds. As she recorded the periods of their pulsations and their apparent magnitudes, how bright they appeared from Earth, a groundbreaking correlation emerged. She observed that the brighter Cepheid variables had longer pulsation periods, while dimmer ones had shorter periods. This was not a random scatter, it was a clear, mathematical relationship. In 1912, Leavitt formally published her findings in the Harvard College Observatory Circular, titled Periods of 25 Variable Stars in a Small Magellanic Cloud. In a concluding statement, almost as an afterthought, she succinctly stated, "A straight line can be drawn representing the relation between the brightness of the Cepheid variable and the logarithm of its period." This simple sentence described what would become known as Leavitt's Law, or the period luminosity relation. Her discovery was monumental. It meant that if astronomers could measure the pulsation period of a Cepheid variable, they could then determine its true intrinsic luminosity. And if they knew a star's true luminosity, by comparing it to its apparent brightness, they could calculate its distance from Earth. It was, effectively, a cosmic standard candle, a reliable measuring stick for the vast distances of space. At the time, the prevailing view was that the Milky Way constituted the entire universe. Scientists had no accurate way to measure distances beyond a few hundred light-years, let alone determine the scale of the universe itself. Leavitt's law provided the first reliable method to do just that, opening up the possibility of mapping the entire cosmos. Part 3. The Universe Expands, Hubble's Confirmation, 1913 to 1929. Despite the profound implications of her discovery, Henrietta Leavitt's work initially received limited public attention. She continued her meticulous work at Harvard, but her deafness and the societal norms of the era meant she remained largely in the background. She was a woman working in a male-dominated field, and the significant implications of her findings were often attributed to her male superiors. However, the scientific community, particularly those engaged in the burgeoning field of astrophysics, slowly began to recognize the power of Leavitt's law. One of those who immediately grasped its significance was Edwin Hubble. Hubble was an ambitious astronomer at Mount Wilson Observatory in California. For years, he had been observing mysterious spiral nebulae, fuzzy, spiral-shaped objects in the night sky. The great debate of the 1920s revolved around whether these nebulae were simply gas clouds within the Milky Way or island universes, entire galaxies far beyond our own. To settle this debate, Hubble needed a way to measure the distances to these nebulae. He knew that if he could find Cepheid variables within them, Leavitt's law would provide the answer. After painstaking observations, primarily using the powerful 100-inch Hooker telescope, he identified Cepheid variables in the Andromeda Nebula, M31, and other spiral nebulae. Applying Leavitt's period-luminosity relation, Hubble calculated the distances to these nebulae. His results were staggering. Andromeda was not a cloud of gas within the Milky Way, it was a separate galaxy, millions of light-years away. This discovery, published in 1929, irrevocably changed humanity's understanding of the cosmos, proving that the universe was far vaster than anyone had imagined, filled with countless other galaxies. Hubble's work, which confirmed the island universe theory, directly relied on Leavitt's law. Without her foundational work, he would have had no reliable method to measure those immense distances. Later, Hubble would use the same principle to observe the redshift of galaxies, leading to his groundbreaking discovery that the universe is not static, but expanding. Leavitt's law was the essential first step in this revolution. Part 4. The Unacknowledged Genius, 1930s present. Despite the monumental impact of her discovery, Henrietta Leavitt never received the recognition she deserved during her lifetime. She passed away in 1921 at the age of 53, having made her most important discovery a decade earlier. Her obituary, while acknowledging her contributions, buried the significance of her law among other achievements. In 1925, for years after her death, Swedish mathematician Gösta Mittag-Leffler considered nominating Leavitt for the Nobel Prize in Physics. He wrote to Harlow Shapley, who had taken over directorship of the Harvard Observatory, requesting more information about her. Shapley, in his reply, did not even mention Leavitt's deafness and downplayed her direct role, stating that the work was done under my direction. He also informed Mittag-Leffler that Leavitt had passed away, making her ineligible for the prize. The nomination, therefore, never materialized. This episode highlights the systemic biases of the era. Women's contributions were often minimized or attributed to their male supervisors. Leavitt was not a professor, she did not lead her own research group, and her status as a human computer meant her brilliant insights were easily overlooked by the scientific establishment. It took many decades for her name to emerge from the shadow of Hubble and others who built upon her work. Today, her legacy is finally being honored. Astronomers worldwide acknowledge Leavitt's law as one of the most fundamental discoveries in astrophysics. From understanding the scale of our own galaxy to measuring the expansion rate of the universe, the Hubble constant, Cepheid variables, and thus Leavitt's law, remain indispensable tools. Her story is a powerful reminder of the countless human computers and unsung heroes whose meticulous work and profound insights laid the groundwork for scientific revolutions, often without receiving the credit they so richly deserved. Henrietta Leavitt, a deaf woman working in obscurity, provided humanity with the ultimate measuring stick, allowing us to finally comprehend the true, awe-inspiring scale of the cosmos.